real big pleasure to introduce our last speaker of the this final session of the Imagine seminar. So it was our third season. So it's good anyway when you look back on how many talks we have organized. So the last speaker of this season is Dr. Leon Bungardt. So Leon is currently a postdoctoral researcher at the Hausdorff Center for Mathematics in Bonn, where he moved very recently. So I think it was beginning of June, as he said. So he received his PhD summa cum laude from the University of Erlangen in September 2020, under the supervision of Martin Burger. So his thesis was awarded with the PhD prize of the biennial French-German Mathematics in Imaging Conference, so the MIA conference that took place last January. So we congratulate Leon on that. And Leon, let me say, is also one of the organizers of the online series on the mathematics of deep learning, and one of the past organizers of the OneWorld seminars on the mathematics of arbitrary data sources, which kept us with some company during the first lockdown. So his research focuses on applied analysis, and in particular in the connection of techniques from inverse problems and PDEs on graphs to data science, machine learning, and imaging. And today, Leon will tell us about his recent work on a Bregman learning framework for sparse neural networks. So before leaving the stage to you, Leon, just one comment on the questions. So Leon said he's happy to take questions during the talk. So if you have any, just write them in the chat and I'll read them out loud to Leon. Or you can just wait till the end of the talk and interact with him directly. So Leon, now is really your moment.
Yeah, thank you very much, Luca, for this kind introduction. It's a great pleasure for me to be able to give this last talk in this great seminar series. So thanks again to the organizers for inviting me. Okay, then let's get started. I hope you all see my screen. I will speak about a Bregman learning framework for sparse neural networks. And this project is joint work with my colleagues from Erlangen, Martin Burger, Tim Reuth, and Daniel Tenbrink. All right, so let me first present you the structure of this talk. I will first speak about some motivation, which will be subdivided in two questions. First of all, why in the first place are we interested in sparse neural networks? And secondly, how can we use Bregman iterations in order to compute or train sparse neural networks? Then in the first main block, I will present you our algorithm, which is called the Linbrack algorithm. This is the baseline approach. I will first speak about initialization issues a little bit, and then I will present you the baseline algorithm. And then I will also talk about some extensions of our baseline algorithm using momentum terms and ADAM, in fact. And then here in this second main block, I will speak about the analysis that we were able to do for our algorithm. So this will be basically convergence analysis of a stochastic optimization algorithm. And then in the end, I will show results both for training sparse neural networks, but also for a different application, namely for neural architecture search, which is all about computing network architectures which are most suitable for a given task. And then in the end, I will conclude the talk and present some outlook. All right, then let's get started with the motivation. First, I wanted to speak about what are the advantages of sparse neural networks and what are sparse neural networks in the first place. Okay, so sparse neural networks are neural networks which have a comparably low number of neurons or a comparably low number of connections between neurons. So this is a qualitative definition, I would say. And the good thing about that is that sparse neural networks have much lower computational complexity and also memory requirement than standard neural networks, which might have millions or even billions of parameters. And this leads to two things. First of all, you can train them significantly faster, and also the online performance, that means applying a network, is much more efficient if you have a sparse network with only a small number of parameters. And this leads to the second benefit, namely that you have much less energy consumption and also CO2 emission, which is a thing which is often overlooked in the context of neural networks. They require huge amounts of data storage and also operating GPUs in order to train and run neural networks produces a lot of CO2, so it's really worthwhile, I would say, to be able to compute sparse neural networks with good performance. The second property, which is quite desirable, is that sparse neural networks are less likely to overfit the training data and hence are believed to generalize better. And this is just due to the fact that they have a smaller number of free parameters. Okay, so in 2018, a specific hypothesis has been proposed by Franklin and co-authors, and this hypothesis was called the lottery ticket hypothesis. And this sort of claims and also empirically proves, let's say, that each dense neural network contains, in fact, a sparse, equally performing subnetwork. And of course, this is good news. And so the only question is, how do you compute such a sparse subnetwork with equal or almost equal performance to a dense network? So let me just illustrate these differences between dense and sparse networks again, using this simple image. So this might be a standard neural network with 4 layers, an input layer, 2 hidden layers, and an output layer. And this is a fully connected network, which means that you have connections from each neuron to each neuron from the next layer. In contrast, a sparse neural network is depicted on the right-hand side. And this has maybe less neurons. So here there's only 2 instead of 3 neurons, and also less connections between the individual layers of the network. Good. So now the big question, of course, is how can one obtain sparse neural networks? And of course, our approach is not the first approach in the literature to compute them. So let me present you with some of the established approaches. There are, in fact, basically 2 different paradigms for computing SNNs. The first one is dense to sparse training, which basically means that you start with a dense network and you make it sparse. This is why it's called dense to sparse. And 2 popular techniques here are pruning. So pruning just means that you take a given pre-trained network and you remove some of the weights, let's say in the weight matrices, with small absolute value, hoping that they don't have a big influence on the outcome of the network. And hence you can sparsify your network by removing small weights and at the same time retaining a good performance. And what is typically done is that you remove some networks, which is called pruning, and then you train the sparser network again to improve the performance a little. And then there's also traditional L1 regularization, which basically comes from the lasso method, which has been well known in the community for quite some years now, which just means that you during your training you add some L1 penalty term to the empirical risk functional, let's say, penalizing a large 1 norm of the weight parameters of the weights in the network. And this way you can also, during the training, reduce the number of non-zero weights in the network. Okay, so this is dense to sparse training. Then there's also the opposite approach, which is a sparse to sparse training, and which has the favorable property that you don't need to have a dense network in the first place, but you can start from a sparse network and make it a little bit non-sparser, but still keep a sparse network, let's say. And this is mostly done using evolutionary training, which basically means that you add some connections in the network randomly and decide whether you need them or whether you throw them away again. Okay. However, the problem with this approach is basically that it's not mathematically, it has no mathematical foundation, or only very little mathematical foundation, and it's hard to see whether this approach does something meaningful or not. Hence, we proposed a different sparse to sparse training method based on an inverse space flow idea, or in other words, based on Bregman iterations. And we're not the first ones to apply Bregman iterations to neural networks. In fact, there has been a paper where the authors used a split Bregman scheme, which is not Bregman iterations, but kind of similar to compute sparse neural networks. And also in this paper by Benning and co-authors, the authors use Bregman iterations for computing networks whose weight matrices have low rank. Okay, so this is not directly connected to sparsity; it's rather connected to sparsity of singular values. So these ideas have been around, but they haven't been applied to really train sparse neural networks. Okay, so what is the idea? Basically, it's very simple. You start with very few non-zero parameters, And then you successively add new parameters such that an energy, or let's say the training cost or the training risk, is significantly reduced. So you don't add the parameters in a random way. You do this based on some gradient criterion, in fact. Okay, so this is the qualitative idea. Let me now tell you a little bit about Bregman iterations. I know that many from the inverse problems community, of course, know Bregman iterations very well. Still, let me repeat a little bit of what they do. So they were basically invented in this paper by Osher and co-authors in 2005 for the task of image denoising, or a little bit more general image restoration. And so what happens is you take some noisy image and you want to denoise the image, but you don't start from the noisy image itself. Instead, you start from a very simple image, namely a constant image. It can be the 0 image or the mean value of the pixel values here. And then you successively add details to the image until you end up with a solution which is which captures most of the interesting features of the original image, but does not have noise. Okay, so this is the visual idea. You can even go one step further. So this was the visual idea. Let us now cast this into formula. So what Bregman iterations for image denoising do is they start with a constant image, for instance, equal to 0. And they also have a second variable, which is the subgradient variable called p. And you also initialize this guy with 0. And then you do an iterative denoising scheme, basically. You first denoise an image, but not the original image f, but instead the sum of this original image f and the subgradient variable. However, in the first step where the subgradient is 0, you just denoise your original image f. Okay, and you got a denoised version. However, typically you choose quite a small tau, which means that you have a very large oversmoothing in the beginning. And then what you do is you take the subgradient variable and subtract from it the residual of the solution you have just computed and the original image. So basically, this is supposed to contain the noise, which is in the original image. And then you update your subgradient variable and go back to the first step, and you alternate these two steps. Okay, and this then leads to this inverse scale space behavior that I've just shown to you, going from a very simple image to a more and more complicated image. Okay, and this iterative scheme here, in fact, can be reformulated using the so-called Bregman distance. Okay, and you can reformulate it in a very elegant way. Namely, the first step here is equivalent to, in fact, denoising the original image. So you have u minus f here, but then you don't have the regularization functional j, which can, for instance, be the total variation, but instead you have the Bregman distance with respect to this regularization functional. And I will, on the next slide, introduce you the Bregman distance. And yeah, the second step just remains the same. So basically, yeah, you can reformulate this scheme here in such a way. And this then also opens the door to generalize it to more interesting or more general applications than image denoising. Okay, let us shortly speak about the Bregman distance, which is in blue here. So the Bregman distance of some convex functional j is defined as the following way. So it depends, or it measures the distance between 2 points, u and v, which are in the domain of the functional. And it also depends on a subgradient p, which is here in the superscript. And this p should be a subgradient of j at the point v. So the sub-differential here is just a generalization of the standard gradient to convex functionals, which are not necessarily differentiable, but you can think of this as being the gradient. And then what the Bregman distance computes is the difference between the function value at u and the linearization of the function evaluated at the point v. Okay, so let me visualize this. You have the functional j here, this is the black line, and you have 2 points u and v. And if you want to know the Bregman distance, you should linearize your function around v. You get this green line, and then you measure the distance between the function graph at u and the linearization graph. And this distance here is precisely the Bregman iteration. And for convex functionals, this is always non-negative. I think I said Bregman iteration. It's of course the Bregman distance, this red line. Okay, and let me just remark that if you choose j as the quadratic functional, so j of u is u squared, then this Bregman distance just reduces to the squared Euclidean distance. Okay, and in fact, the Bregman distance is not a distance because it does not satisfy the triangle inequality. It's also not symmetric. The only thing that it is non-negative. Okay. Good. So we had this scheme here with the Bregman distance, which came out of the denoising problem. Okay. So let us now call this this term u minus f squared. Let us call this a function L. And then you can rewrite this scheme in the following way. Here you have your function L. Okay. And down here you happen to have the gradient of the function L. Right. So the gradient of this function at the point uk plus 1 is precisely uk plus 1 minus f. So you can rewrite the scheme in the following way. And now you see that you can, in fact, apply this to any functional that you want to minimize. It doesn't have to have this quadratic form here. You can take whatever you want to, and still this scheme here makes sense. Okay. So this is good news because it allows us to apply Bregman iterations to more general loss functions, let's say, than this quadratic one. Okay. However, there's a slight problem with this Bregman iteration here. Namely, if you have a general loss function L, which is not necessarily the quadratic one, then this becomes very expensive or impossible to solve, because in every iteration, you have to solve a minimization problem here in the first line, involving this function L and the Bregman distance. And if L is a very complicated function, then you have to use a whole optimization algorithm just for evaluating one iteration of the Bregman iterations. This is, of course, terrible, because then it becomes very ineffective. Hence, what people did quite some years ago is to introduce linearized Bregman iterations. So this happens, they arise in the following way. You first linearize your function L of u here around the old iterate, around uk. So you have this expression here. And in fact, you plug in this linearization for L of u here. However, then you have a problem, namely this linearization is, of course, a linear function, and this Bregman distance back here is typically not a coercive function. So you might have problems with existence of the minimum here. So what you have to do is you have to replace your function j in the Bregman distance with something which is strongly convex. And you do this by adding this small quadratic term here, which yields that this function j delta is a strongly convex function. And then you can show existence of minimizers here for this initial problem. Okay, and plugging in these two things, you then end up with so-called linearized Bregman iterations, which have a very simple form. First of all, one renames the variables because this variable p was in the subdifferential of j. However, now we have a variable v, which is in the subdifferential of j delta, this regularized functional, so we call it a v instead of p. And you see that this update in v is very simple. You just take the old subgradient and you subtract from it the gradient of the loss function at the old iterate. So this is a bit like an explicit Euler discretization. And then you recover your initial variable or your primal variable u by applying the proximal operator of the function j, not the function j delta, but indeed the function j here to this subgradient variable. Okay, and you see that this is a fairly good scheme if you want to apply it to complicated functions, because this proximal operator here, it can be easily evaluated if j is some standard regularization functional like TV or the L1 norm whatsoever. And this explicit gradient step here is also fairly easy to evaluate for complicated loss functions. That's why we basically utilized these linearized Bregman iterations for our neural network application. And let me remark here that this formulation, which I wrote down, is very compact. And in fact, in the literature, this one has only been derived for a problem from compressed sensing, where L, again, has a quadratic form and J is equal to the 1 norm. However, one can show quite easily that using these linearization techniques here in the initial version of the Bregman iterations, you always recover this very simple form here. Okay. And this may remind some of you of proximal gradient descent. However, there are some differences, namely proximal gradient descent does not have two variables, but just one. So you have u here, and the proximal operator depends on the step size, on this optimization step size tau here. And these seem to be very small differences, but in fact, the difference between Bregman iterations and proximal gradient descent is huge. as we will also see in the numeric section. Good. Just a small remark. You can also derive a time continuous limit of Bregman iterations if you send tau, the step size, to 0. And this time continuous limit is called the scale space flow. If you do this for the original Bregman iterations, so not the linearized ones, then you will basically see that these are an implicit unit discretization of this ODE here, which is called the scale space flow. And yeah, the linearized Bregman iterations in turn are an explicit Euler discretization of an inverse scale space flow, however, with respect to this functional J delta, not with respect to J itself. Okay, J delta was this elastic net type regularization of J. Okay, so let me emphasize here that this is not a gradient flow. These two equations are not a standard gradient flow. However, if you choose J, the regularization function here, as the quadratic Euclidean norm, then indeed you see that the second line just reduces to P equal to U. And then this is indeed the standard gradient flow. However, this inverse scale space flow is a generalization of gradient flows, of Euclidean gradient flows. Good. So let us now see how we can use this Bregman framework and the inverse scale space framework in the context of neural networks. And yeah, now we have a very important step. Namely, from now on, I will use the variable theta in order to encode network parameters instead of the variable u, which in the inverse problem community stands for images. Okay. So yeah, I know mathematical symbols are a mess and notation is a nightmare, but bear with me that now we use theta instead of u, just in order to be consistent with the typical notation in neural networks. Okay, so the question is, how do we apply these linearized Bregman iterations, which are repeated here, for training sparse neural networks? Firstly, one should choose J, the functional here, as a sparsity enforcing functional, for instance, the one norm, or let's say a group one norm more generally. In fact, you can, you have quite a big freedom in how precisely you choose the regularization functional. However, it should somehow contain a one norm in order to generate sparsity. And then secondly, you just choose this loss function L here as the empirical risk of your neural network on a training data. Okay, this sounds fairly easy. However, there are some catches, which make these a difficult problem, in fact. First of all, L is the empirical risk functional is typically non-convex, or it's always non-convex if you work with neural networks. And evaluating the gradient of L is too expensive if you have a large training data set. And secondly, initializing all parameters with 0, as you would do it for standard Bregman iterations on images, does not work. I will tell you in the next slide why this is why this doesn't work. So one already sees that one has to do something with the Bregman iterations in order to make them applicable. Good. So let us first speak about this initialization issue. And for this, let us assume that we have a standard feed-forward neural network consisting of L layers, which are all the composition of a affine function and an active nonlinear activation function. And you have these weight matrices WL and the bias vectors BL here. So it would be appealing to just initialize the whole process with W equal to 0 and B equal to 0, which is a fully sparse neural network, and then successively update all the parameters. However, this does not work, and this is well known in the machine learning community, since initializing all the weight matrices equal to 0, which is missing on this slide, I'm sorry, yields an unbreakable symmetry. And this is due to the fact that each neuron then has the same effect on the outcome of the network, and hence during the back propagation it will get the same weights. So you will basically most of the neurons will then act in the same way, and you will lose the expressivity of your large neural network. So this is well known and a big problem. So what we do is the following. We choose some initialization of the weight matrices WL tilde at random, and then we just mask them with some Bernoulli variables, meaning that our initialization WL is just let's say the element-wise product of these random weights and a mask whose entries are distributed according to Bernoulli distribution with some probability R between 0 and 1. So if R is equal to 1, then this is just a matrix containing only ones. So you have you just have a random initialization. If R would be equal to 0, then the mask would be equal to 0. And this is the case which doesn't work. Okay. And so the question is now, how do you choose the WL tilde? So at random is not yet a clear definition. And what you in fact do, which is well known in the community, also you should initialize these weights with 0 expectation. But the question is, what do you do with their variances? And indeed, you can do a formal computation which tells you how to initialize the variance such that you avoid the nasty effect of exploding and vanishing gradients during training, which basically means that your optimization algorithm that you use for training the neural network does not make any progress or divergence. And to avoid this problem, we showed that you have to choose the variance in a reciprocal way with respect to this constant R, which steers the initial sparsity level of your initialization. So R is the initial sparsity of the network, and you have to choose the variance in a reciprocal fashion. And here there's some function alpha, which depends on the activation function you use. For instance, if you use the sigmoid activation, you should choose this function alpha as 1 over the product of the old number of the number of neurons from the L-1 layer and the number of neurons of the L layer. So this was also derived in papers by Goodfellow and co-authors. However, here we showed that you have to use this reciprocal constant here in order to avoid this exploding and vanishing gradients. Okay, so this was the initialization bit. Then what do you do with the loss function? I already remarked that the loss function is too expensive to evaluate, and hence you just do what you always do in training neural networks. You replace the empirical risk on the whole training data set by a batch loss function, which just evaluates the average loss of your network on a batch, which is a subset of the training data set. Okay, so let me just talk you through this expression here. Small l here is a loss function which compares how well the output of your network at theta to some training input x, how well this agrees with the training output y, and you check the average over the whole batch which you sample from the training data set. And if b has a very small number of elements, then this is of course a feasible function to evaluate and also to take gradients of. Good. So then using these strategies, we already obtain our baseline algorithm Linbrack, which does the following. So first of all, this delta constant, which appeared in the regularization of the function j, we choose this equal to 1. And in fact, this always does a good job. And for quadratic problems, you can in fact show that delta does not have an influence at all on the long-time behavior of the algorithm. Okay, then we initialize the parameters in a sparse way, as I've described on the previous slide. And you also initialize the subgradient variable v as a subgradient of the initial values. And then you just iterate. You do a loop roll epochs, and each epoch you sample a mini batch b from the training data set. And then you do 3 things. First, you do a back propagation step, which in mathematical terms just means that you compute the gradient of this batch loss function in the old parameters, which you have from the previous iteration. Then you use this gradient in order to update the subgradient variables. So this is the first step of the linearized Breakman iterations. And then in the second or last step, you recover the parameters of the network by applying the proximal operator to the subgradient variable here. Okay, so this is the very simple baseline algorithm. And in fact, let me just remark that the complexity of this algorithm is basically the same as the complexity of standard stochastic gradient descent, because they only differ in one line, namely this proximal step here. However, if the function j is a one-norm type function, you always have an explicit or an analytic expression of the proximal operator, so this does not add to the complexity of the algorithm in general. Okay, let me speak about a few variants which we also proposed. Firstly, you can add some momentum. And this happens in the following way. So again, you first recover your variable g as the gradient of the empirical loss function. And then you compute a momentum vector, taking in account a convex combination of the direction where you came from and the direction of the gradient that you've just computed. So this basically is a linear combination, as I said, from the old direction and the new direction. So it's an inertial term. And this inertial term you then use to subtract it from your subgradient variable v. Okay, and then you get this update scheme. And beta is between 0 and 1 here. And if beta is equal to 0, you just recover the standard Linbrack algorithm from the previous slide. Yeah, and typically you choose beta a bit smaller than 1 for good results. The second thing that you can do is you can also employ the famous Adam algorithm, which has been very popular in the last years for training neural networks, and which basically does a combination of a moment step, as we do it here, or a momentum step, and a so-called bias correction step. I don't detail the algorithm here because it's quite long. However, what we in fact did, we proposed a generalization of the Adam algorithm, which includes these Bregman steps, so the 2 variables, the primal one and the subgradient variable, and this proximal step that we've seen. And this gives them the what we call AdaBreg algorithm, which also seems to work, in fact, better than the standard baseline algorithm, and also better than the momentum algorithm, as it is observed for standard stochastic gradient descent algorithms. Okay, let me now tell you a little bit about the analysis which we were able to do for our problem. And the analysis that we did is for the baseline algorithm, Linbrack. Because if you try to analyze the momentum algorithm or even the Adam algorithm, things become terribly much more complicated. And in fact, this is subject to future work. And even for standard stochastic gradient descent schemes, there's not too much out there in the literature which really quantitatively analyzes these algorithms with momentum or Adam. So let me tell you what we did here. First, we rewrote our Linbrack algorithm in an abstract form. So in fact, we did analysis for a standard stochastic, an abstract stochastic Bregman iteration. So this does not use any structure coming from the neural network. It's just a stochastic version of linearized Bregman iterations, which has not yet been analyzed in the literature. So we could contribute a little bit on that. And so let's rewrite the algorithm in the following way. You first draw a random variable. So this random variable basically corresponds to the elements of the training set that you would like to sample in each epoch in order to generate your batch. And then you have this subgradient update here, where you use this function g, depending on the old network parameters and this random variable. And this function g is supposed to be an estimator of the gradient of the loss function that we're actually interested in. And here estimator means estimator in the stochastic sense. I will speak about this on the next slide in more detail. And then the last step is just the proximal step, which turns the subgradient variables into the primal network parameters by applying the proximal operator of j. Okay, so this is our algorithm in abstract form. And in order to analyze it, we need some assumptions, of course. And I split these assumptions into assumptions on the gradient estimator, so on this function g of theta, which appears here, and in assumptions on the loss function L, which we're actually interested in. Okay, so and I must say that the assumptions are basically standard assumptions that you can find in every optimization paper, and this is good news. So basically for analyzing Bregman type algorithms, you don't need terribly more complicated or severe assumptions than for standard stochastic gradient descent. So the first assumption that we have is that the gradient estimator is an unbiased one, which simply means that the expected value of this gradient estimator taken over the random variable omega equals the gradient of the loss function, which we would like to minimize. So this is called unbiasedness. And then a second assumption regards the variance of the gradient estimator. So the variance is the term here on the left-hand side. So the expected value of the square difference of the estimator and its mean, or its expected value here. And we assume that this variance is bounded by some finite constant, sigma squared. And in fact, in standard machine learning applications, this is always the case. And basically, sigma is proportional to the reciprocal size of the batch. So if you choose a very small batch, then the sigma is huge. And if you choose your batch equal to the whole training data set, then the sigma is equal to 0. Okay, so in most applications, you have this bounded variance assumption. And yeah, the prototypical example which is used in applications for this gradient estimator is just, as I said, the gradient of the batch loss function. So you choose some batch dependent on the random variable here, and then you just evaluate the gradient of the empirical loss function on this batch. Okay, and this fulfills these two properties or these two assumptions. Okay, then we need some assumptions on the loss function curly L, which we would like to minimize. And also these assumptions are somewhat standard, at least the first one. Namely, here we assume L smoothness of the loss function, which can be expressed in this inequality here. And what it means is that at every point, you can, let's say at every point theta, you can approximate your function L with a quadratic function given by this expression here. And this quadratic function majorizes the function L for all other points. Right? Okay, so this means that the graph of L lies below a parabola, and the curvature of the parabola should be given by this constant L here. And you can rewrite this in terms of the Hessian matrix in case that your loss function is twice continuously differentiable, then L is just the norm of the Hessian matrix, or the largest norm of the Hessian matrix over all points in the space. Good. And in fact, one should say that this assumption here is implied by Lipschitz continuity of the gradient. So if the gradient of the function L is a Lipschitz continuous map, then you have this assumption here. This is well known in the optimization community, and I just give it as a remark here. So you don't need C2, you basically only need that the gradient is Lipschitz. Okay, and then the second assumption is related to a convexity assumption. Of course, here I can already hear the alarm bells ring, because in the empirical loss function for a neural network is typically never convex. Okay, so let me do two remarks here. First, typical arguments say that around your local minimum that you would like to converge to, or maybe around your global minimum, your function might be convex. So you might be able to show this. And then if you start your algorithm close enough to this minimum, then you have this convexity assumption. Okay, and of course, in general, loss functions are not convex, but I will comment in the end on how you might circumvent this problem. Let me also remark that you don't need the convexity for all of the statements. You basically only need it for convergence of the iterates of the thetas, and not for convergence of the loss function itself. Okay, and so what we demand here is that basically the other inequality holds true, namely that you can bound your loss function from below by a parabola, or by something which is similar to a parabola. So you have this quadratic type functional here, where this function d here can take two different values, let's say. So the first case is the Euclidean case. So here the function d would just be the Euclidean norm. And then you basically have the reverse inequality of this inequality here, however, with a different constant nu, which is smaller than L. And this is what's called a strict convexity in the literature. However, in our Bregman case, we can show a bit more if we have a different kind of convexity, which is adapted to the geometry of Bregman iterations. And this becomes the Bregman case, where basically this function d here equals a Bregman distance, namely the Bregman distance of this regularized functional j delta. Okay, and for instance, if j is equal to 0, so if you don't have any regularization at all, then these two quantities coincide, right? But this convexity here is a stricter convexity. However, in finite dimensions, you can in fact show, if you choose j equal to the 1 norm, that this is equivalent to the Euclidean convexity. In infinite dimensions, this might not be the case. It's a stricter assumption, and it allows us to prove stricter statements, but also in this standard Euclidean convexity case, we can prove convergence statements. Okay, so let's look at what we can do first. Let us, for notational convenience, define the so-called symmetric Bregman distance, which is nothing but the sum over the two Bregman distances with flipped arguments. So I already said that the Bregman distance is not symmetric, so you can flip theta bar and theta here to get two different quantities, and adding them up yields a symmetric expression, of course, and this is what we call symmetric Bregman distance. And using this symmetric Bregman distance, we were able to show the following loss decay. Using the assumptions on the gradient estimator, which is standard, and the assumption on the L smoothness. So we don't use convexity here, just the L smoothness. So we were able to show the following inequality, namely the expected value of an iterate plus this term here, which is a non-negative term, can be bounded from above by the expected value over the old iterate plus a term which contains the variance of the gradient sampler. So sigma here was the standard deviation of the gradient sampler from the true gradient. And this is a statement that you would also have in this form for standard stochastic gradient descent without this Bregman distance here. And in fact, let me remark that this is a generalization from what was shown for non-convex Bregman iterations in a paper by Martin Benning and co-authors, where they basically don't have this noise term here because they consider the deterministic Bregman iterations. So we were able to generalize these results here. And then let me just remark that if you have some assumptions on the step sizes, for instance, that the square of the step sizes is integrable or summable, then you can also show decay rates for this Bregman distance here, which is then useful for the further convergence analysis. This can also all be found in our paper. However, in this talk, I won't go into detail here. So let us now speak about convergence of the iterates. Okay, let me just go back for a second. Here we basically showed that up to a small stochastic error, the loss function decreases. Okay, so let us now see whether also the iterates theta k converge to something. And ideally, we would like them to converge to a minimum of the loss. So, and first we will show L2 convergence under this standard Euclidean strict convexity assumption here. So where this function d was equal to the squared Euclidean norm. So we have this assumption, plus we need some condition on the step sizes. First, the step sizes should be square summable, but they should not be summable. So this fact that they are not in L1, so not summable, just means that the sequence has infinite length. So, or in principle, your algorithm can discover the whole space. This you always need for these kind of algorithms. But you should be square summable, and a prototypical example is this harmonic step size condition here. And we also need them to be non-increasing, which is also a standard assumption, I would say, in optimization. And then what we can show is that a subsequence of our Bregman iterations converges to theta star, which is the global minimum of the loss, which exists since we are in the strictly convex case here. And so here you see that using Euclidean convexity, you can basically show Euclidean convergence here, but only up to a subsequence. Good. And let me remark that all these statements are true in infinite dimensions as well. So I speak about Euclidean norms, but what I actually mean is norm in the Hilbert space. Okay, so this is the L2 convergence that we basically have more easily. Then let's see what we can get if we have some stricter assumptions. Namely, if we use this Bregman strict convexity. So we have all our standard assumptions with the Bregman convexity here. And here we only need that the step sizes are not summable. So we don't need any condition on the squares of the step sizes. So this is more general here. And then what we can show is that the whole sequence, theta k, converges in this Bregman distance of this regularized functional J delta. And let me remark that this also implies that it converges in the Euclidean distance. Basically, because you can split this Bregman distance here in the Euclidean norm plus an additional term depending on J. So this in particular implies the Euclidean convergence, but it's a stronger convergence statement, which comes from the fact that we use the stronger convexity assumption here. And you can also get a convergence rate in this case, namely if you choose the step sizes as being this harmonic sequence here, you have a convergence rate of 1/k. Okay, and this is also consistent with what is known for stochastic gradient descent. Okay, let me now show some results, some numerical results. So first, I will show you a standard sparsity application where we use our algorithms to train a sparse neural network. So what we do here is we set up a multi-layer perceptron consisting of several layers, trained on the MNIST data set for classification of handwritten digit images. And the regularization function J is just chosen as the sum over all the one norms of the weight matrices. So this is, if you write it out, it's just the sum over all parameters in the network, over all weight parameters in the network. Okay, so then we get a couple of curves. So let me talk you through this. Maybe first look at the top left curves. This is the train accuracy. So how many images we are correctly classified on the training data set. And we compare here a couple of algorithms. The first one, the black line, is standard stochastic gradient descent without any sparsity regularization. Then we have three of our Bregman algorithms, which with different values of the regularization parameter, which basically is contained in this loss function here. And then we have proximal gradient descent, which is a seemingly similar but quite different approach to sparsity regularization. And we see that basically the train accuracy after a few epochs becomes 100%, both for the standard stochastic gradient descent and also for our Bregman algorithms. ProxGD needs a bit longer here to optimize the train accuracy. Okay, train accuracy is not that interesting, but similar things hold true also for validation accuracy using an unseen validation data set. Of course, here the curves are a bit more oscillating because these images which are used here, they do not enter the training data set. And here you can see that basically with this pink Bregman algorithm, you only have 0.5% drop in accuracy. However, with the pink algorithm, you only use less than 10% of the weights. So in stochastic gradient descent, you would use 100% of all weights. So it's an extremely dense network. And here we can use only less than 10% and still get a very high validation accuracy. And yeah, here in this left plot, you can nicely see the inverse scale space behavior of the Breakman algorithms. So all these solid lines, they increase for the L1 norms, they increase during the iteration. However, for stochastic gradient descent, for proximal gradient descent, this is not true. So first, the L1 norms increase a little bit and then they decrease again. So you don't have this inverse scale space behavior here. And this can also be seen in the non-zero entries, which is basically the L0 norm. So here, proximal gradient descent and also SGD immediately destroys sparsity and then retains it again after some iterations. Whereas in contrast, the Bregman algorithms are basically monotone. So they successively add more and more parameters, which is this inverse scale space behavior. Okay, you can also do this for more interesting neural networks, for instance, for convolutional neural networks. And what we choose here is we choose our regularization function equal to a group sparsity, which is the one norm of the two norms of all convolutional kernels. So what this group sparsity regularizer enforces is that you only have a few active convolutional kernels. And you see the results quite nicely. So here we show you all convolutional kernels in the first layer of quite a large convolutional network that we trained. In the beginning, you might have two non-zero convolutional kernels, and then during the iterations, more and more kernels are added, but you still retain a sparse convolutional network, meaning that only a few kernels are non-zero. And yeah, what we visualize here are in fact not the kernels, but the feature maps, meaning if you put an image, here it's an image of a t-shirt, into the network and then see what do the convolutions do with it, then you get these small images. And this is what we depict here. But you can nicely see the inverse scale space behavior of our algorithm, which successively increases kernels to improve the accuracy, but still it retains a sparse neural network. All right, yeah, we also applied this to ResNets, which are quite huge residual neural networks. And we did here some computations on the Cypher 10 dataset, which is more challenging than MNIST or Fashion MNIST. And here you can also see that with our Breakman algorithms, you can generate really sparse neural networks with only 3% or 3 to, let's say, 9% of parameters, but still you have quite a high test accuracy of 90%, whereas with the full dense neural network with, I believe, 12 million parameters, something like this, you get these test accuracies, which are a bit better. On the other hand, the network is much more dense here. So we really gain something here. And we also compared ourselves to standard lasso approaches here using an L1 type regularization. And there you don't get sparse neural networks. You have to do some additional thresholding step at the end. Okay, so some images, because you can, as I said, you can also apply our algorithms for a different task, namely for neural architecture search, which is all about computing architectures of neural networks. So basically seeing how many layers do you need, how many kernels do I need, how many neurons do I need. And here I show you some pictures generated for different tasks. So here's a denoising task and a denoising and deblurring task. And in the left column here, and the left column there, we use an autoencoder to solve these tasks. And in the right column, we used a residual autoencoder. And you might be able to see that the results for the residual autoencoders are a bit better than for the standard autoencoders. So you have sharper edges, you have a bit better contrast here. So the question is, can we train our networks that they automatically discover the architecture that they should have? So whether they should have residual connections or how large the layers should be, something like this. And indeed, this is possible with our Bregman method. So here in this initial example, we trained just a standard multi-layer perceptron on this deblurring task. And here I plot the layer sizes after or dependent on the iterations. So what you see here, the input layer of always has a size of 28 squares, something like this, which is the size of the MNIST data set or of an MNIST image. And then you see that over the iterations, the layers become a bit larger. However, they don't blow up to the full size, and you get a nice autoencoder-like structure here after 100 iterations. So our network here automatically learns to converge to an autoencoder. And you can also do this. Quantitatively and do it several times from the algorithm several times in a stochastic way, and compare. Take averages. And in fact, you always get this autoencoder-like structure here for the denoising and also for the deblurring task. Good. And we also did this for residual type networks, where we allowed the network to have some residual skip connections, but we penalized them with a sparsity term. And so what we show here are the layer sizes. So here you do get an autoencoder, but it's a different one. So you first reduce the dimension quite a lot, and then you linearly go up again. Similar things for the deblurring task. And in these matrices down here, we visualize the skip connections. So here, a red entry means that there's a skip connection from the third layer to the fourth layer, for instance. And here we see that we only get quite a sparse number of skip connections. And we also see that we get skip connections with positive values and with negative values, marked in blue and in red. So this sort of tells us that standard ResNets, which always have a skip connection value of 1, not necessarily the best architecture. You might also want to have negative skip connections. This is something that has also been observed in the literature. So here we can confirm it with our neural architecture search method. Okay, so let me conclude this quickly. What we've seen today is Bregman iterations can successfully be applied for training sparse neural networks and also for neural architecture search. I showed you some analysis of stochastic Bregman iterations. I showed you that it can be applied to standard network architectures, and you can also do neural architecture search. Future work includes sparse training, which means that you train your net only a few parameters of your network, so you really exploit the sparsity computationally. And you can also try to prove convergence in the fully non-convex setting using predictor-Yoyashevitz type techniques. Okay, so let me conclude this talk. I would like to thank my collaborators, which are depicted here. Here you have the papers. We have a nice GitHub if you're interested. And of course, you can always ask me questions via email. Thanks for the attention. Now I'm ready for your questions.
Thanks a lot, Leon. It was really, really interesting. And we got already a few questions. So I think the first one who asked a question was Maniko. So I'll allow Manny to speak.
Mm-hmm. Yeah. Oh, hi. Very interesting. Okay. I'm always been a fan of Bregman because of total variation. Okay, so I like your approach of directly using a sparsifying regularizer during training, because as a practitioner, I cringe when I thought after compressing the network, I had to retrain, because most of the work is actually in validating and testing the generalization and stability of the model. So, but it's very good result that you can only show that 3% or so is enough now. But it doesn't really help with the training efficiency, right? Okay, that's my question. I assume the per epoch training cost is much higher, right? And you still need to have the entire tensor actualized, just that there are a lot of zeros, and then GPU doesn't like the sparse matrix representation, especially not one the sparsity pattern that keep changing all the time, right? So I guess that will be great if we actually can exploit that sparsity pattern, actually in reducing the actual number of parameters upfront in some or I don't know how to do it, but that seems to be the next challenge for us. Also, by the way, is your PyTorch code available? Okay,
yeah,
thanks.
it is available here in this GitHub link. Okay, can I reply to this question? You raised a couple of very good points here. So first, I would like to say that the training cost per epoch is exactly the same as for standard stochastic gradient descent, because applying this shrinkage type proximal operator does not contribute to the complexity. So the complexity of our algorithm is the same as for standard stochastic gradient descent. However, as you correctly suggested, you can try to exploit the sparsity during the training to make it more efficient. However, there's a small problem with this approach, and this problem is the following: that a priori, you don't know which of the network parameters you might need in the next step. So you basically have to compute the gradient of the loss function in all parameters to then see which of these parameters are large enough such that they are important enough to be included in the training. However, what you can do, basically Tim, my collaborator, came up with this idea, and we would like to try it in the future, is you do a sparse training step, which means you only update with respect to a few parameters. You do a couple of training steps in a sparse way, and then you do one step with the whole set, with the whole tensor, with all the zeros, to see where you will need the new weights. And then once you have fixed the new weights, you do again a couple of training steps with these fixed weights. And with this strategy, we hope that you can exploit the sparsity. However, exploiting sparsity straightforwardly is not that easy as one might think, even with the Bregman approach. But with this, it might work. Did this partially answer your question?
Yes, because one competitive approach is to use an approach like ShuffleNet, right? Mm-hmm. Yeah, because ShuffleNet is allowing us to use to be agnostic to the exact connectivity needed upfront, but still do not bias the actual information flow, right? So I think that's the main problem. How can we have an architecture that initially are agnostic to the connectivity or flow, but then still allow adaptation? I think it's a puzzle. I don't know how to solve it.
Okay. So I think maybe we carry on with questions because we have many, which is good. So the following questions was coming from Yuri. So Yuri, I allow you to talk. Yeah, go ahead.
Yeah, thank you so much. Thank you, Leon, for the nice talk. I think my question is a little bit arbitrary, but still. There is a theorem by Combat that every function sigma that is 0 at 0 and monotonically non-decreasing and maybe something else, that this corresponds to, that this is a proximal operator of something, of some convex functional. So you in effect have two different proxies here. First of all, you have your prox that corresponds to your J, and another prox which is implicit through your activation function. I was just wondering if there could be any interesting interaction effects between the two.
Yeah, that's a good point. I mean, what we did in our algorithm was a bit basically we neglected the network structure. We just work with a non-convex function, and then to this we can apply our algorithm. And this non-convex function then happens to be the empirical loss function of a neural network. However, exploiting the explicit structure of the loss function might then enable us to do what you say and to sort of see an interaction. But at the moment, this would be pure speculation, because as I said, you don't necessarily see the structure or the architecture of the network in the training scheme. But in fact, let me just remind on this. You can always rewrite Bregman iterations as a neural network. This is something which has been shown in a paper by Martin Benning and Martin Burger. So basically, you could write this whole process as a Bregman iteration of Bregman iterations or something like this. Yeah. But at the moment, this is just speculation.
Okay, thank you.
Yeah, you're welcome.
Okay, so there was another question from Ozan Oktem. So Ozan, I'll allow you to talk in case you want to ask your question directly. Otherwise, I can just read it.
Hi, yeah, I mean, it's a misunderstanding. I'm not Ozan Oktem, I'm Shubhadeep Mukherjee. Yeah, I joined the meeting by clicking a link on the Google Calendar, and the event was created. Wasn't, so I don't know.
That's no problem. You can ask your question anyway.
Yeah, thanks, Leon, for the very nice talk. So I was just wondering, so how does the final trained network compares with, let's say, a dense network with fewer parameters, and which is trained in the conventional way? So, for example, if I had started with a neural network which has like as many neurons and as many weights as you finally end up training using this sparsity-based regularization. So how does it compare with that? And then I was also wondering, did you think of any greedy learning algorithm, something which is, let's say, analogous to orthogonal matching pursuit in sparse approximation, which would maybe try to approximate one weight parameter at a time and try to maximally reduce the loss function, something of that sort?
Mm-hmm.
As opposed to using a convex regularization based penalty?
Yeah. Okay. So with respect to the first part of your question, we didn't include these numerical experiments in our paper for some reason, but indeed, if I remember correctly, then the networks which are trained with the Bregman algorithm, they had better performance than the networks which were initialized with the same number of layers as the final outcome and so on, and then trained in the conventional way. But as I said, we don't have the quantitative results in our paper, but I still remember that it was better. And you should also take into account that a priori, of course, you don't know which network size or which architecture you would like to use.
Yeah.
So,
true.
I mean, you could do this as an academic comparison, but in practice, it's hardly feasible, I think. But it's a good point for sure. With respect to the second question, we didn't think about any greedy algorithms yet. However, what we thought about was replacing the L1 norm with the L0 norm, because we basically only need the proximal operator, and the proximal operator of the L0 norm is a hard threshold. Yeah. Exactly. And this also works. However, it's quite prone to be stuck in local minima, as it's already been observed in the literature. So you can, of course, also do standard regularized training schemes, for instance, proximal gradient descent with the L0 norm. It's a bit difficult, I would say. And we have the feeling that the L1 norm is really doing quite a good job here already.
Mm-hmm. Yeah. Thank you.
Yeah, you're welcome.
Okay, so we are a little bit late. So what I would recommend is there are other questions, though, so maybe I would recommend like Linda and Byung Wo Hong to write directly to Leon their questions. So let me thank Leon again for this very nice concluding talk of our third season of our Imagine seminars. And I wish you all a wonderful summer, and we keep you updated in the following weeks with the details of the next season, which will start again in September. So on behalf of all the organizers, the old one and the new ones, I wish you all a very good summer. Thanks again, Leon.
Yeah, thank you, Luca.
Bye.
It was a pleasure. It was big fun. And yeah, you can